All right, so now we're going to be wrapping up chapter 2 in this last video here. We're going to move on with the idea of the derivative of a function as a function. And so far what we've been talking about is, given some function f of x, how to find its derivative and what that means, f prime of x. But because the derivative of a function is a function in its own right, a function of the same variable x, we might be able to take the derivative of that derivative. Okay, so in other words, f prime prime, which we also notate this way, f double prime. We call that the second derivative of f. Okay, so notationally we can write that this way. If I've already evaluated a derivative, here's Leibniz notation, dy dx, then we've been calling that the derivative, but we could also call that the first derivative. If I apply a differential operator to that d dx, then I'm taking the derivative of that derivative, which gives me the second derivative. And this is the notation in Leibniz notation that we use for that. Notice that we use what looks like exponents, even though technically they are not exponents. It's just notation. It looks like d squared y over dx squared. We don't read it that way. We just say second derivative of x. Okay? So let's do an example where we want to find a second derivative. Now, let's see, I didn't talk about different notation. So I don't think I wrote down different notation for this, but if we have y equals f of x, this is one type of notation, but we could also write that this way, y double prime or f double prime of x. Those are all acceptable notations for the second derivative of a function. And there's others, but those are the ones that we're going to be using. So here, I have a function y equals x cubed plus 2x, and we're going to find y prime and y double prime. Okay, so let me start with y prime. Y prime, again, that's just the derivative or first derivative of our function. Limit as h approaches 0 of x plus h cubed plus 2 times x plus h minus x cubed plus 2x all over h. Okay, limit as h approaches 0. If you know your binomial theorem from intermediate algebra or pre-calculus or college algebra, wherever you would have learned that, that's going to help you expand things like this much faster. Without having to do a bunch of work, I already know that that's equal to x cubed plus 3h x squared plus 3h squared x plus h cubed. Okay? If you know your binomial theorem, you can do those things much, much faster. So I recommend reviewing that if you need to. Plus, I'm going to distribute the 2. 2x plus 2h. I'll distribute that negative in as well. Minus x cubed minus 2x. All over h. All right, I'm seeing x cubed cancel here. So negative x cubed and positive x cubed. Does anything else cancel? Yeah, I have a 2x here and a minus 2x. So that means I'm left with 1, 2, 3, 4 terms in my numerator, all of which have an h in them. So I can cancel that. I'll lose that h. I'll lose one of those. That becomes an h squared, and I'll lose that one. So this becomes the limit as h approaches 0 of what? 3x squared. Plus 3hx plus h squared plus 2. Okay. Because h is approaching 0 and I have a polynomial here, I can substitute 0 in directly for my h's, which is going to cause this term and this term to both go to 0, leaving me with just these two terms. 3x squared plus 2. And again, I mentioned this before, in the very first section of chapter 3, we're going to look at shortcuts for evaluating these functions, derivatives of these functions. Once we cover the shortcut that we would use in this case, you'll be able to go from here to here literally in like 2 seconds. You won't need to do all of this work, okay? That's y prime. But what we need now is y double prime. That's the derivative of this derivative. What is y double prime? Well, it's a derivative in its own right? Limit as h approaches 0. But now the function that I'm using when I'm taking my derivative in the limit definition is this function, the one that I just found. So that would be equal to 3 times x plus h squared plus 2 minus 3x squared plus 2 all over h. That's equal to the limit as h approaches 0. I'll expand this out and multiply by 3. I'm going to get 3x squared plus 6hx plus 3h squared plus 2. Distribute my minus sign in. Minus 3x squared minus 2 all over h. Look for cancellation. So I have a 3x squared and a negative 3x squared. I have a 2 and a negative 2. And all that's left are these two terms up here, each of which has an h in them. Now I can cancel my h. So that leaves me with 6 plus 3h. 6x plus 3h. So that's going to look like this. 6x plus 3h. I can do direct substitution. H equals 0 here, which is going to cause that term to go away. And 6x is what I'm left with. I think I was off screen there for a little bit. Okay, so here's my y prime, here's my y double prime. If you notice, I graphed both of those. Okay, so the original function y is this red one because it's the cubic function. Cubics have that kind of wavy sort of look to them. Y prime came out as a quadratic, so that would have to correspond to that parabola. And y double prime came out to a linear function, 3x. So this must be y double prime down here. And we can explore all the same relationships that we did before. Notice that my cubic function, the red one, it's pretty clear that it's increasing the whole time. It continues having a positive slope at all times. It becomes a little bit shallower of a slope as we get here, but then becomes steeper as we go here. So that indicates that my derivative, y prime, should lie completely above the y-axis, or sorry, the x-axis, because it remains positive at all times. Y double prime, what is that? Well, y double prime is looking at the derivative of y prime. And y prime being a parabola, I can see it has a decreasing slope. Its tangent lines are all negative until I get to 0, which is why y double prime is completely below the x-axis until we get to 0. And then my parabola starts having an increasing trend. Its tangent lines are all positive after 0. So after 0, all of my function values for y double prime are positive and increasing. Okay? So that corresponds to what we would have expected to see there. All right, it's our last page here. So because a derivative represents a rate of change, then the second derivative of a function represents a rate of change of a rate of change. And the easiest way to see what that looks like is to go back to our example of position and velocity. What is the rate of change in velocity defined to be? Well, we call that acceleration. If your velocity is changing, that means you're either speeding up or you're slowing down. And we think of that as accelerating. If you speed up, you're accelerating. If you're slowing down, oftentimes we call that decelerating, but for this class, we're going to put that under the umbrella term of acceleration. So if at some given time t, we define acceleration to be a of t, then the way that we're thinking of derivatives here, a of t would be a rate of change of v of t. Acceleration is a rate of change in velocity. So it makes sense to define a of t, my acceleration function, to be the derivative of my velocity function, v prime. Okay? But velocity is already a derivative. It's the derivative of a position function, which we could call s of t. So v prime is the same thing as s double prime. And that means I could think of acceleration as the second derivative of my position function. Okay? Now we can define higher derivatives than just second derivatives. We can go beyond that. So what if we continued on and we defined, let's say, the third derivative of a function, or the fourth derivative, or the fifth derivative, or so on and so forth. You get to each new derivative simply by taking another derivative of whatever came before it. So by definition, the third derivative of a function is the derivative of the second derivative of that function. And we can use any of these notations: y triple prime, f triple prime of x. Here's Leibniz notation. Notice I'm using 3's instead of 2's here to indicate that I'm talking about a third derivative. Okay? If we go to even higher derivatives, fourth, fifth, sixth, and so on, we stop using prime notation because it gets really cumbersome to write all of those. If you're taking the 100th derivative of a function, I don't want to have to write 100 of these primes. So we start to change it, and instead we turn it into a superscript. It almost looks like an exponent, but we put parentheses around it to indicate we're talking about a derivative. So the nth derivative of a function looks like this: y, and then in the superscript, n in parentheses, whatever n happens to be. Okay, let's do an example where we're finding a third and fourth derivative of a function. So starting with this one, we're given y equals x cubed plus 2x. Now notice we've already dealt with this function back here. We found the first and second derivatives of this function. So I'm going to remind myself that the second derivative of this function was 6x. This guy, using what we've already found, is equal to 6x. So what would the third derivative be? The third derivative of this function is the derivative, with respect to x, of the second derivative. Okay? Or in other words, d dx of 6x. But what is that equal to? That's the limit as h approaches 0 of 6 times x plus h minus 6x all over h, which is equal to the limit as h approaches 0 of 6x plus 6h minus 6x all over h. 6x's cancel out, h's cancel out. This is the limit as h approaches 0 of 6, which is simply 6. That should be no surprise, by the way, because what does this function look like if you graph it? It's a linear function. So the line would look like the graph would look like a line with a slope of 6 everywhere. That's exactly what this is telling me. The slope of this function at any given point that I plug in is 6, right? So that's exactly what we would have expected to see. What about my fourth derivative? Well, this would just equal the derivative of my third derivative, or the derivative of the function 6. Now, think about this for a second. What do you expect the answer to be? It's a constant function, 6, y equals 6. The graph of any constant function is a horizontal line. We would expect the slope to be 0 everywhere. So I'm expecting this to come out to 0. But using my limit definition, the limit as h approaches 0, if I plug x plus h into this function, I have nowhere to plug it in directly. So it's a constant function. No matter what I plug in, I get a 6. It's the limit of 6 minus this function evaluated at x, which is still 6, over h, which equals the limit as h approaches 0. 6 minus 6 is just 0. 0 over h, which is equal to 0, and that limit would equal 0 as well. So I got the constant function 6 here, constant function 0 there, okay? That is going to wrap up chapter 2 for us.